This is a demonstration to show an analogy for Coulombs law using magnets instead of charges. We have here a setup where we have a box of Legos that is holding in place a force sensor. The force sensor measures how strongly this arm over here is being pulled on or pushed on. The force sensor is connected to this data collection box over here. That's going to give us the numerical values of the force. Over here we have, on the end of the arm, we've glued a strong neodymium magnet. And then there's a little cork spacer on the end there. That's just to prevent the magnets from snapping together. Because on the other side, we're going to use this Lego piece to bring magnets closer or further away from the magnet on the force sensor. We're going to move those magnets on this piece that we're going to put down at different places. I have it set up for both repulsive and attractive possibilities. We're going to do repulsive first. All right, so we're going to zero this, we're going to zero this guy out. And now we're going to place our magnet that's in the repulsive direction down here. The distance from this magnet to this magnet is about 5 millimeters to begin with. So we're going to graph that as we collect it. All right, so we're going to keep that point. And this is about 5 millimeters. I know that because I measured it ahead of time. All right, so we have a data point beginning right here. It's a little hard to see in the shot. Okay, so we have a data point there. Now we're going to move this guy back one of these little Lego divots. They're called studs in Lego world. That increases the distance about 8 millimeters. Okay, so we're going to keep this now. So 5 plus 8 is 13 millimeters. All right, so now we have 2 points. We have a point up here and a point down here. So this was our first force. This is our second force as we move outwards. Now we're going to move this back another 8 millimeters. So we're up to 21. Keep. (21 millimeters). All right. So we've got, that's our first one, our second one, our most recent one. We're going to increase the distance another 8 millimeters. So now we're at 29. All right. And you can see that's our most recent point. And then the last point we're going to take is way out here. These magnets are strong enough that they can still be creating a force even at this distance, 37. All right. So that's our force distance curve that we've obtained for the attractive case between magnets. Now we're going to do it in the reverse direction, or rather the inverse setup. Now we're going to use the attractive magnet. And this is where they really jump together and we really have to use that. That spacer comes in handy. We're going to stop this and we're going to restart it to collect the data now for the attractive case. So we'll hit the play button. We're going to append this data. We're going to keep a data point here at 5 millimeters. And the new data point is down here. So now this is positive force up here. Now we're measuring a negative force for this data point. It's almost -4 newtons for the 5 millimeter distance. But all of our original data points in the attractive case, in the repulsive case were positive. This first one for our attractive case is negative. Let's see if that trend continues. So we move this guy out 8 more millimeters, keep 13, right? So that's still negative, but it is decreasing in value. So it's a negative, about a negative 0.7, right? Do this again. Keep, we're now at 21. This again, keep, 29. Keep 37. All right, so now let's take a look at our data. So we can see that in our first case, the repulsive case, all of our forces were negative, but they decreased towards 0. In our attractive case, all of our values are negative, all right, whereas before they were positive. Now all of our values are negative here in the attractive case, but they also decrease in value towards 0 as we go to greater distances.